My name is Brent Griffin. I am a principal research scientist at Voxel 51, and this talk is called Pixels Are All You Need, Utilizing 2D Image Representations in Applied Robotics. In contrast to the previous talk, this is going to be a little bit more focused on mobile manipulation robots. So I want to start with a quote, and that's that vision without action is merely a dream. Action without vision just passes the time, and vision with action can change the world. And so if we look at visual AI, one definition of that is the subset of AI processes that processes visual data to provide humans, physical systems, or software with the necessary insights for informed decision-making and action. So I think the physical systems portion of this definitely applies to robotics. One thing I found in my own work in the past is that when I was doing work purely in computer vision, in this example, doing video object segmentation, this is really meaningful in terms of human insight and information, but this really isn't designed to be used for a physical robot application. On the other side of some other experience I've had in robotics, working in two-legged bipedal locomotion, purely focused on control, no external sensing of the robot, interesting, difficult problem. But was this robot ever going to be able to go and do some task in an unstructured environment? No. And so if we look at a lot of traditional robotics, the same holds true where you see a lot of people developing new hardware, new techniques, and they'll use fiducial markers or structured environments to make up for the gap of not having an actual visual AI or perception system, with the idea that at some point in the future, we'll just have a computer vision person come in, provide that signal, and everything will work just fine. But my experience has been that the expectations of robotics is often kind of out of line with what computer vision is able to apply in terms of reliability and what is the level of representation that is being output. And so this is where a lot of emphasis that I put on subsequent to that work was looking at how can we design visual AI in robotics in a way that's cohesive such that we're using reasonable signals from computer vision that aren't necessarily a full 3DOF with the full model of the objects that we might be interested in. And in robotics, we're not controlling or designing our system such that we need all that information. We actually design our system such that we can operate from pretty low fidelity basic representations that are more reliable. And so some examples I'm going to talk about that today are in visual servo control and vision-based manipulation. And these are ways that visual AI can serve robotics. But one thing I like to emphasize to the community is there are also ways that robotics can help computer vision. So another thing I'm going to talk about today is depth for motion and detection. And this is where we take odometry information from a physical system, provide it to a visual AI system, and now it can infer 3D information about the environment that in turn is going to help that robotic system. Another really good example of this is self-supervised depth estimation, if you're familiar with any of that work. And another thing I want to point out, and I think, this is partially evident from the previous talk, is that visual AI is really dependent on a massive amount of data. And so if we look at ResNet, which was referenced in the previous talk, that was originally trained on 1.28 million images. But if we look at more recent models and foundational models, that scale has increased substantially to something more like 400 million images in the case of CLIP. And so this kind of issue or this scale or this hunger from visual AI to get more and more data, I think can actually be served by robotics. You saw the case of AVs collecting data in the previous talk. Two other robots I've worked with, Digit has 7 cameras, HSR has 4. And so if you think about it, a single robot, not even a fleet, just a single individual robot can collect ImageNet scale data within just a few hours. And this isn't even leveraging an entire fleet. This is a robot that's deployed to a specific workplace, a specific environment. It's able to generate data that's relevant to the task that it's performing, and it can generate that data at a massive scale. And if changes are happening in the environment, it can capture that as well. And so this is something that I'm also very interested in. How do you design a robot system such that it's collecting its own data, using that to improve its own visual AI system, and then that in turn helps the performance of the robot? And I'll call this robot-supervised learning towards the end of my talk. And so to get started, I'm going to go ahead and start with the visual servo control and vision-based manipulation. There's a lot to get through, so I'll just go ahead and get right to it. So the motivation for this vision-based manipulation work was from a grant that we got with the Toyota Research Institute, and they also supplied a human support robot, or HSR, that you can see on the right. And HSR is intended to help with caring for disabled individuals. Also in Japan, they have an aging population. This also occurs much throughout the world. And so human support robots could be a way to help mitigate any kind of issues associated with these societal problems. Now, when we first got our HSR robot, though, as far as they demonstrated up to that point, it really wasn't able to work in unstructured human environments. And again, kind of going back to that classic robotics problem, they would use things like fiducial markers in the hope that that would be solved at some point in the future by computer vision or some other approach. And so we agreed to help TRI address this limitation and also participate in a few HSR challenges. So a little bit about the HSR challenges. It was the same organizers as the DARPA Robotics Challenge in 2015, and it really required teams to operate outside of their areas of specialization and integrate with many other technical components to perform end-to-end real-world tasks. So you can just be a control person, you can just be a computer vision person, you can just be a manipulation person. You really had to find a way to put all these things together in a way that could operate in a set of conditions that was defined by TRI, not what you wanted to do for your experiment for your paper. And this included teams from Stanford, University of Michigan, MIT, Berkeley, and all the other schools that you see below, as well as others. And so this was actually a pretty large-scale challenge with a lot of participants. The first challenge itself was relatively straightforward. You would log into a live video meeting. You had 1 5-minute trial to perform a task, which was pouring blocks onto a metal tray. They'd be scattered. You wouldn't get to choose where they were positioned. And then you had to place each block on a shelf behind the tray based on its color to a specific shelf. And the idea was that they're going to start with a simple challenge and then make these much harder in the future. So when we first started doing testing on this, we decided to use the RGBD camera on top of HSR's head. And we would just use the image channel to segment objects based on color. And then we would use the depth channel to specify things about the 3D geometry. So here's an example where I'm going to say HSR, pick up the large red block. It identifies red segments in the image, and then it's going to use depth to determine the geometry of that object. It identifies a large red block. It comes up with a manipulation plan and goes to execute it, and it has a misgrasp. And so this can happen for a variety of reasons. Low degree of freedom in the arm. It has to move the base. The RGBD camera becomes occluded, so it can't have updates. And essentially, this robot wasn't really in a good place to use that RGBD camera. But even if you are using an RGBD camera that's maybe a little bit more designed with manipulation, there's still limitations if the objects are in close proximity or if you have something like a reflective tray. And so in addition, it was also unlikely that we're going to be able to scale the simple color-based recognition system to real-world objects, which was the goal of the whole project. So we went to plan B, which was using RGB-based grasping. And thankfully, Toyota had put a camera directly on the gripper of the robot. And so our idea was, let's use that camera. You can see an example image on the left to locate objects and then grasp them. And one way that we could do this was using visual servo control. There's a lot of existing literature and tutorials on this. It was very easy to pick up. Like most control problems, it starts with an error. And that's going to be some set of image-based features S and their desired position as star. Now, if you look at what was existing in the visual servo literature before, again, classical robotics, use fiducial markers, work on the control problem. But we had had this previous experience doing video object segmentation, and we knew that we could generate these reliable signals for objects, regardless of if they were articulated, interacting with the environment, or had a moving camera. And so we had the idea segmentation image features. And in this way, we'd be able to operate in those unstructured environments on real-world objects. And so once we had this error defined based on the segmentation of objects, we had to relate that error to actual controls that were going to actuate the robot. And the way that we learned to do this control process, details aren't important. You can go read the paper later if you're interested, but it was using what we call Hardeman-Broyden update. And the significance of this update is it essentially allowed us to have a segmented object in view, start with an initialization of weights that's essentially an identity matrix, and within 14 time steps, learn to center on the object with that grass camera using the actuated base. And the significance of our specific update is when we would try to use previous updates that had been designed, the robot would not learn fast enough. It would require too many time steps and it would essentially crash into the wall behind HSR before it learned an actual policy that it could use. Now, the next part of this is after centering on an object, we would actually have to grasp it. And so what we did is recognizing that the segmentation mask itself is just a projection of this object in 3D space into the image plane. What if we additionally projected the gripper into that same image plane and we looked for the area where the overlap between the gripper and the mask itself would be minimized So we could do an antipodal grasp. And what this does is it pretty much guarantees that you're going to be gripping the narrowest part of the object, which is most likely going to give you a good chance to perform grasp closure. And we found that this approach works for many, many different YCB objects and the HSR challenges. So when we went to the first challenge, we were able to place all of the blocks that were put onto the tray. This blue block here was one of the most difficult ones because even after grasping the block, we had to place it behind the tray itself. And so you really had to have the arm extended and then use the pseudo omnidirectional functionality of the base to get in a position where you could actually place this block. And we were able to do this not that fast, but in a time of 2 minutes and 50 seconds. Now, the team that came in second place did not move the robot at all. They placed the tray on the side. And what they did basically was rotate the base, grab the object using the RGBD camera. And this is how they mitigated that issue with executing a grasp plan from that RGBD camera with motion of the base. They just took the motion of the base out of it and modified the way the challenge was set up. But to their credit, they're able to place all 3 objects. Now, if we look at the third place team, there was no tray. And in addition, they used Vicon reflectors on every object. And even in this setting, they were able to place one of the 3 objects. And that was the last team to be able to place any of these objects. And so the significance of this is it is really hard to put all these things together as a comprehensive system. And I think this is what TRI learned from doing this first challenge. So in the second challenge, they kept things mainly the same. They did add a banana as another object that you had to place in the trash. But using video object segmentation, recognizing and grasping this object was not an issue. And the third challenge, they created more complicated objects. They also allowed us to use voice commands with the robot, which we did using a custom Alexa app. And we were able to place all these objects, but the kitchen tongue that was in the back. So another cool thing about this approach for visual servo control from segmentation is we can really learn different policies for any set of actuators on the robot. And so we did this for a number of different camera configurations and a number of different actuators. So just to show you one example, we learned a policy where HSR could track segmented objects with its head. And then once we've learned that policy, we can essentially freeze the weights, stop learning. And now we can track objects that are actually moving throughout the environment. So here you see me moving throughout the lab, and HSR is tracking me with its head camera because all it needs is a segmentation mask of something like the hooded sweatshirt that I'm wearing. And so we ended up using this in the fourth challenge where we had to place objects all throughout the lab. And essentially what we did is if there was an object that HSR could not find, it would ask for help. It would look for me, and then I would move to the area of the room where the object was. And then it would go back to using its normal grasp policy to then go and find that object. In the fifth challenge, they made things harder again. We had to work with large deformable objects. This required us to regrasp objects to continue to place them into the cubby. And then the really impossible part of this challenge was they asked us to pick up a chip bag off of the ground, place it inside of a cup, and then place both of those objects on a shelf. And you have, again, one chance to do this during a trial. We used a sucker that was on the back of the gripper for HSR that could pick up flat, light objects. We would finally locate the cup once we found it from segmentation. We would locate it using 2 grasps, and then we would actually go and place the bag inside of the cup. And I'm happy to say that we were able to do this during the actual challenge. And then the last challenge, they made it so that we had to work with unknown objects that had not been seen before. We used a general segmentation algorithm to segment all these objects on the table. And then we used the interactive capabilities of the robot to determine if the objects were deformable or not. And then that's how we would determine if we were able to place them through the 2-inch cross-section or if we had to basically place them to the side and ask for help later. So segmentation is one kind of low fidelity representation at this point. Detection is one that is even cheaper in terms of annotation and arguably have models that are better performing. And we were able to replicate all this work with detection as well as segmentation. And while we were at it, we also revisited the way that we learn these visual servo controllers. And in this example here, HSR is going to perform a series of predetermined motions. And within 13.3 seconds, it finds a set of visual servo control weights where it can track this racquetball. Again, just learning from a single click of annotation to be able to detect the racquetball, 13.3 seconds of robot time. And because it's detection, it's able to run much faster. And so the robot can very accurately track this moving object. And we can also perform mobile pick and place at about 120 picks per hour. So here the robot is grabbing cups and then placing them in the same color bin that corresponds to that cup. while we're moving the bins. And this is using a combination of the head camera and the grass camera with the robot. So the significance of the challenges are that we can perform mobile manipulation with ordinary objects using detection or segmentation. We were the first team that used visual servo control. We open sourced all of our code with the 4th challenge. And by the 6th challenge, 80% of the teams were using visual servo control. And so this had a substantial impact in how this mobile manipulation community thought about what kind of representation should you use, how should you do control for mobile manipulation, and resulted in a substantial amount of tech transfer to Toyota Advanced R&D as well. So that wraps up using this simple visual AI detection segmentation for the benefit of robotics. I want to talk about depth from motion and detection as one example of how we can use different signals from robotics to help visual AI. So in this scenario, we have HSR. It's observing this shelf with a bunch of different objects on it, and it wants to be able to go grab these, and it's just having something that provides a bounding box for each one of these objects. So it has no 3D information from an RGB camera, but what it can do is perform motions in a controlled manner such that it knows what the differences in camera pose are. And when we combine that information with the bounding boxes, we can actually determine what the depth is. And to make it a little bit more clear how this is possible, if you think about a model where you have an object in view of a pinhole camera, again, that's just going to be a projection into the image plane, and we can put a bounding box around that object, and it's going to have some height, h1. And so this can be the scale of the object in the image plane. Now, if you move the camera, and again, using the pinhole camera model, we can use optical expansion along with that change in camera pose, and there's an analytical solution to solve for depth. And the same thing is true with motion parallax. So we don't just have the scale of the bounding box, we also have the offset location in the image plane. And so if we move the camera laterally, we can look at the way that the position of the bounding box offsets, and then we can use motion parallax with that known change in camera pose to similarly solve for an analytical solution of depth. So we can do this using both motion parallax and optical expansion. But where this gets really complicated is if the object is moving, if you have errors in detection, or you have more complicated motions. And this is why we created what we call the object depth via motion detection data set. And this is to train an LSTM model that can take a series of observations. Each observation takes a change in camera pose, as well as the height and width of a bounding box and its lateral and vertical position. And when we feed in a series of these observations to this network that we train, we are then able to predict the absolute depth. Now, one issue with this is if you train on data that is on the scale of, say, 1 to 10 meters, and then you try to use this in autonomous vehicle operation, the network has not learned to predict the distance of objects, say, at 100 meters away. And so you can also reformulate this as a dimensionless problem. There are more details in the paper for how to do this, but the benefit is you now have a network that you can use in autonomous vehicle applications or mobile robotics or other applications as well, using the same lightweight LSTM. And the way that we generate the data that we train this network with is very simple. We basically have a simulated object. We have a set of camera intrinsics, and we move where that object is relative to the camera. We know what the change in camera pose relative to the object is. And so we can create this extensible training data. But to make it so that this model is more prepared to go out and movement errors, so that when those things occur on the robot, the LSTM network has already learned to basically ignore these errors and look at the overall volume of data coming in and still make an accurate decision. And so here's some results of one of those networks. Again, single network being applied with a camera phone or in an autonomous vehicle setting or a mobile robotics case. We just change what is the source of that odometry information, whether it's kinematics, GPS, or velocity of the vehicle. Now, all this data is available to generate in your own projects. If you're interested, follow on the link below. It's very fast. You can generate hundreds of thousands of examples in fractions of a second. And there's no principled reason why you also can't apply this work to segmentation. The main complication is when you're creating that extensible training data, you have to come up with a bunch of different segmentation mask shapes. But we were able to do that using this extensible training data configuration, using random variation of segmentation masks like you see in the examples there. So you can find depth via motion detection or segmentation, and here's some overall considerations. These networks are very simple. You can perform inference on thousands of objects we found in about 4.3 milliseconds on a very simple GPU. And it's low cost because the training data are basically free. and they generalize across domains. But the disadvantage is you're going to need a network like faster RCNN or a video object segmentation network that's actually going to provide those detections or segmentations of the object. And this gets me to the last part of my talk, which is this area of robot-supervised learning, where we're going to have the robot create that kind of training data on its own for free. So this was really motivated by work we did with TRI for their Woven City project, which is they're going to create this entire city that has robots and people living together synergistically. And the way that they're going to do that is they're going to design these environments that humans live in to have automation in place. And so I've shown examples of how robots like this can move throughout the environment and do manipulation on objects. But one thing that is missing here is having the robots learn from those interactions with the environment and use that experience to improve their own vision system and their own capabilities. So if you think about it, the robot's using perception and control to perform tasks in the environment. It's then going to be able to collect data while it's performing those tasks. And what we want to do is take some of this data and improve our underlying perception model that's learning from this data so that we can update our vision system as the environments change or the tasks get harder. Now, some of our colleagues at TRI took on this problem by looking at doing a bunch of domain randomization and simulation with a preset of 3D object models. And they demonstrated that for a tabletop setting, they could go and perform manipulations from this learned representation and simulation. The issue was if the environment changed or they had objects that had not been captured, this system would no longer work. Now, the work that I've shown previously with visual servo control manipulation required that we collected some data, separated some training examples, maybe spent about a minute per segmentation image or about 7 seconds per bounding box that we applied, but it required human annotation. And so this is a limitation. Now, on the other hand, with this work, what we're going to do is we're going to have it so that the robot collects its own training examples and additionally annotates those objects so that it can update its own vision system. So this is a little bit like having your cake and eating it too. And so the problem is that the robot's going to interact with a new object. And what we're going to do is generate a pixel-wise annotated training example that we can use to improve the vision system. And the way that this works is it uses 2 primary systems. One is a foreground background segmentation approach, and the other is learned self-recognition from the robot itself. And so the first thing I'm going to talk about is the foreground background segmentation approach, which we're then going to use to learn how to do robot object segmentation. So the foreground background segmentation approach is just using a kinematic model of the robot and the depth channel on the robot's head along with the RGB image. And so what it does is it collects a bunch of depth images of the robot's arm while it's looking at itself, whether objects are grasped in hand or not. We then project the kinematic points into that depth image, perform a segmentation, and any of those segments that align with the kinematic point that's within the depth range that we expect the robot to be based on the kinematic model becomes a mask that we create from that depth channel. We can then take that mask, associate it with the RGB image, erode and dilate so we have varied levels of confidence. And is this a foreground object, likely foreground, likely background, or definitely part of the background? Perform a simple grab cut segmentation algorithm. And we got very clean segments of either the robot's arm with objects in hand or the robot's arm by itself. So the trick here is we will then have the robot go throughout the lab, different lighting conditions, collect a bunch of data doing self-recognition. We can annotate that data, augment it with different backgrounds, different synthetic foreground objects that we overlay on the picture of the robot's arm. And from that, we can train a network to basically segment the robot's arm in a variety of scenarios. So now when we go back to the foreground background segmentation with the object in hand, we can isolate that object from the robot's arm. And what we're left with is a clean annotation of the object. So here's just a look at, we had 300 original training examples for self-recognition. We augmented that using different backgrounds and foreground elements to 12,000. And we're able to improve over previous state-of-the-art in terms of how accurate were the segmentation masks we're able to generate for these in-hand objects. And more importantly, when we would then take these annotations, feed it back into detection and segmentation, we can improve the robot's performance and its environment based on the tasks and objects that it had there. Okay, so before I get to Q&A, there's just one more thing that I wanted to mention, and I think this was evident in the last talk too, and that's that data is king, and managing data at scale can be a challenge. And so I wanted to talk about one approach that we're working on at 51 of taking any amount of unlabeled data, processing it through an off-the-shelf model, and then learning about the data using the embedding space. So here's an example where I took a bunch of robot data throughout the projects that you've seen so far in this talk, and I just put them a couple hundred images into an embedding space based on clip. And from that, we can start to look at these isolated regions and really start to understand things about the data. Now, me as a domain expert, I understand what these groups of data are going to be likely in advance. But if you do nothing about this data in advance, you could start to infer like, okay, this is in a lab environment with desks and chairs. That's interesting. Okay, there's this outlier area that is clearly in a new environment that I hadn't seen before. Or you could even find parts of the embedding space that relate to specific cameras like the head camera of HSR while it's performing pick and place in the lab. And just to show you a zoomed in example of this, we can also identify images collected from the grass camera in contrast. And as we get down and select smaller subsets of this data, we can do things like isolate clutter out of the images or even isolate individual objects. And so one thing that we've been working on more recently then is how can we take any amount of data, whether it's from a robot application or another application, and actually rate how valuable these are given the context of all the data as it exists in the embedding space. And in that way, we can go back to these subsets if we're interested and automatically select a subset of images that we think are high value, we want to use for training or potentially have be annotated. So with that, that's just one thing that we're working on that we will be talking about and releasing more information for in the future. This concludes my talk. I really appreciate your time. I also want to thank my collaborators at Voxel 51, Jacob Marks and Jason Corso, as well as all the students at U of M that helped with this robotics work. And with that, I'm happy to answer any questions that you might have.